please.
Thank you very much. Thank you all for coming. It's a particular treat for me to talk in this seminar in my hometown. This is the first time I've ever given a talk in New York. And for this reason, I want to dedicate this talk to my teachers at Hunter College Elementary School, which is part of the CUNY system, and also to Harry Ruderman, who taught me a lot of mathematics when I was in elementary school. So this is the Stern sequence, I think, has a lot of interesting aspects to it. It can be studied in a lot of different areas, and you will see names like Gauss, Eisenstein, Minkowski, de Rham, Dijkstra, and a few surprises during this talk. And let's see, here's a definition. Very simple definition. It's a recursively defined function that takes positive integer values. I'll first tell you what Stern did, and then I'll talk about some of the history of the problem and then some of the ways that the sequence has arisen since then. Then I want to specifically talk about some things that my grad students and I have done over the years, mostly what they did in studying and going off in various directions. So first, this is the Stern sequence. This is a picture of the Stern sequence up to 2 to the 11th. And I thought to give you an idea of what it looks like, since the code is 304403, this is the value of the Stern sequence at 304403. Your silicon friends find it very easy to calculate large values of the Stern sequence. What he did was he considered what is called the diatomic array, which resembles a Pascal's triangle with memory, and which I'll call Z of AB. You start with A and B, and then you add A and B, but you keep A and B. Then in the next row, you write down everything and then put down the sum of the elements in between, and so on. And this is what the first few rows look like. Now you can immediately see that the rows are linear in A and B, and that there's a left-right symmetry. So if you started with B and A, you would get the same thing for A and B, but reading from right to left. And in that way, we can decompose Z of AB, RB into this form. So really, everything should matter. The only thing that matters is to know what Z of 0, 1 is. And there it is. Rather than put a lot of pauses in here, in each row, I've let the odd elements be in red and the previous row in black. Each row serves as the first half of the next row. So this defines a sequence, and this, in fact, if you look at the way this is constructed, this is the Stern sequence. This is S of 0 through S of 16. Very easy to write down. This is an example of what I sometimes call airplane mathematics. If you're stuck on an airplane and all you have is a piece of paper and you want to see what you can do, you can just write this down. And then this is the way to describe the elements of what was on the previous page. If you wanted to count S of 2025, you could use the recursion repeatedly and wind up with the number 46. But as we'll see, there are a couple of formulas that let us calculate it directly. If you write 2025 in binary, you notice that there's 6 ones, 1 0, then 1 1, then 2 zeros, and 1 1. If you use these as the denominators in a finite simple continued fraction, if you take them in regular order, you get 46 over 7. And if you take them in reverse order, you get 46 over 33. And these denominators give you general formulas. What 7 is S of 2 to the sum of the denominators minus 2025, and 33 is S of 2025 plus 1. I won't prove it, but it's a fun general fact that the product of the denominators is always congruent to 1 mod the numerator. That's a property from continued fractions. There's a lot of self-similarity in the diatomic array. If you started with S of n and S of n plus or minus 1 and kept going, you would get the sequence that goes from 2 to the r times n to 2 to the r times n plus or minus 1. And this leads to an extremely useful recurrence that also can help you calculate S of n quickly. Now, if you start with 1 and 1, then you get each row becomes, you don't get S of 0, but you get S of 2 to the r through S of 2 to the r plus 1, 1, 1. And you can check 1 plus 3 is 4, 3 plus 2 is 5, 2 plus 3 is 5, 3 plus 1 is 4, and so on. Now, the important thing here is to realize that even though S of 2 to the r is duplicated, each pair S of n plus 1 appears exactly once in here. And I'll use this notation. If AB appears in one row, then AB and A plus B will appear in the next row, as well as A plus B and B. Now, Stern proved two things about these pairs. The first thing he proved was that each pair is relatively prime, and that's an easy induction on the definition of GCD. The second thing he proved was that if A and B are integers that are relatively prime, then there's a unique integer n so that S of n is A and S of n plus 1 is B. And the reason he did not say that this means that S of n over S of n plus 1 enumerates the positive rationals is that Georg Cantor was 13 years old in 1858. So this was an example of a theorem that came too soon. And rather than give a full proof, let me give you an indication of the proof, which will suggest a way to calculate n being given A and B. Suppose you have, since AB and BA appear symmetrically, we might as well assume that A is greater than B. How could 25 and 9 appear in a row? The only way for that to happen would be if 16 and 9 had appeared in a previous row. And then you add 16 plus 9 to get 25. And I'm taking the arrows and writing them backwards just to show you 25, 9 can only come from 16, 9, which can only come from 7, 9, which can only come from 7, 2, 5, 2, 3, 2, 1, 2, and 1, 1. And then working forward from the fact that S of 1 is 1 and S of 2 is 1, you get to n is equal to 187, and S of 187 is 25, and S of 188 is 9. And you could do this with any pair of relatively prime integers. Now, some of you probably have realized that what I'm doing is just calculating in a very, very long way the simple continued fraction from 25. 25 over 9, there are two blue things, so that becomes 2 plus 7 over 9. Then you have a red thing that makes it 1 over 9 over 7, then 1 plus 1 over 2 of 7, and you wind up with that. The continued fraction representation for 25 over 9 is usually written as 2, 1, 3, 2. But as with all rationals, there is a second version because m is always equal to m minus 1 plus 1 over 1. So 25 over 9 could be 2, 1, 3, 1, 1. Now, if you write 187 in binary, you have 1, 1, 1, 0, 3 1s, 1, 0, and 2 1s, and that's the reverse of the coefficients in the denominator. In general, suppose n is an odd number, and this is its binary representation, zeros and ones. Now, I'm ahistorical here because even though binary existed in the 19th century, it wasn't a very prominent feature of mathematics, but it does make things easier. Then this is the theorem. If n is given in this way, then S of n over S of n plus 1 is the formula you get from reversing the order of the denominators. This is the way to calculate S of n and S of n plus 1. The advantage of this as an enumeration of the rationals is that it's very easy to find where a particular rational appears in the sequence, which is not so much true if you do the usual diagonalizing. This is a 19th century result. It certainly isn't mine. this is the usual way it's given, where n has this alternating sum of powers of 2. And for those of you who haven't looked at continued fractions lately, I write out P4 and Q4. P4 has this expression. Q4 would be P3 of x2, x3, and x4. And in the general formula, PM is the product of all the xi's times the sum of reciprocals of the products of non-overlapping pairs, which leads to an interesting thing, because that means that PM is the same if you reverse the order of the denominators. So a more natural question is, what happens if you took the A1 through A2V plus 1 in the standard order? And the answer is that you get S of n over S of 2 to the r minus n, where r is the sum of the HAs. Everything that I've said about these formulas can be fairly easily proved by induction. And more generally, if n is smaller than 2 to the r minus 1, you have an expression like this, which allows you to get rationals in 0, 1. And if m is 0, then this 0 on this flips back and you get the formula you have. I will pretty soon get to the history and context of the Stern sequence, but I want to give a few more of the properties. S of 2 to the r minus 1 is r. S of 2 to the r minus 1 squared turns out to be r squared. For larger r, S of 2 to the r minus 1 to the k is a polynomial of degree k and r, not a particularly exciting polynomial, so I won't write it down. And this is, to me, this is sort of the fundamentally interesting property of the Stern sequence. It always gives you nice sort of random things, sporadic facts. For these three odd integers, S of n squared is the square of S of n. And I have no reason other than it's true. You do the calculation. Now, if you look at the maximum in each row, students like seeing 2, 3, 5, 8 and make a guess as to what it will be. It is the Fibonacci sequence appearing as the maximum in each row. How many odd n are there so that S of n is equal to m? Well, if n is odd, then S of n minus 1 is less than S of n. And we know that the GCD of k and m is 1. And there's a unique n so that we get km. So they're exactly the Euler phi of m odd n with the property that S of n is equal to m. I actually have an application of this later. It's not very difficult to prove that the sum of the rth row is 3 to the r, so that the average value is something like 3/2 to the r. On the other hand, the maximum is a Fibonacci number, which grows like phi to the r, so the extreme values become relatively larger than the average, and you have some spiky things, which I'll be showing later. This is just an absolute gift. For those of you who know recurrences, the left-hand side actually has a second-order recurrence, but the other root is 0. So 0 to the r only shows up when r is equal to 0. And that, again, is an example of sort of the nice things. S of n is even only if and only if n is a multiple of 3. Again, that's easy to prove by induction. In 2008, I showed that if you look at S of n mod d and S of n plus 1 mod d, then it's uniformly distributed among all feasible residue classes. In particular, the probability that S of n is a multiple of d is 1 over I of d, where d is this, I call it a warped Euler phi function. It might have a better name. If one of you knows a better name, please tell me. But rather than taking the product over primes dividing d of 1 minus 1 over p, you take the product of 1 plus 1 over p. Next, the average positive rational number is 3/2. I bet you didn't know that. And based on this ordering, and part of that is this is a fairly easy exact formula to calculate. And a more careful analysis says that if you take the sum up to capital N, it's 3/2 n plus big O of log n squared, which is actually pretty good, pretty small error term. This was one of the things that people in the 19th century thought was really interesting. If you take S of n minus 1 plus S of n plus 1 over S of n, this is always an odd integer. In fact, it's 1 plus 2 times the power of 2 that divides n. And again, that's something that's relatively easy to prove by induction. And finally, I call this a Stern application of Richard Guy's strong law of small numbers. S of 3 to the r is 2 to the r for r equals 1, 2, 3, and 6, and no other r less than or equal to 600. My computer is very patient. And for those of you who prefer matrices, there's a very natural way to express S of 2 and S2n plus 1, S of 2n plus 2 in terms of the pair S of n plus 1. And if you take the power of these matrices, you get matrices that show up in the study of continued fractions. So that's an alternate way of proving the formulas that I just gave. But now I'm going to take a historical interlude. This is Moritz Abraham Stern. He lived from 1807 to 1894, which is pretty impressive for the 19th century. And he had a remarkable life. He was born in Frankfurt to a family of booksellers and rabbis. I hope you can read this article. I'll sort of summarize it. In 1829, he was awarded the doctoral degree with distinction at Göttingen, Gauss having been one of his examiners, and he was made a private docent. He translated books. He wrote popular books. 8 years later, the ministry agreed to pay him a yearly salary with the explanation that, quote, as a Jew, Stern cannot become a professor. In 1840, he was recommended for the position of associate professor, and 5 years later, the ministry said, as a Jew, it is completely out of the question.
It is worth reminding here that being a Jew at the time was a religious choice. You could convert to Christianity, and then you could get your professorship.
Yes, and there were, I'm blanking on the name. There were many people who were ethnically Jewish who had converted for what we'd like to call in the U.S. business reasons. And he finally became a professor in 1859. And he was the first unbaptized Jewish full professor at any German university in any department. I did some research on this just to try to balance things out. The first female full professor at any German university was appointed in 1923. I think she was a soil chemist. And I could not find reliable information about the first Muslim, Hindu, or Buddhist professors, but I suspect those are post-World War II, when the German universities did not dominate research the way they did in the past. He retired in 1885. His replacement was Felix Klein. Stern moved to Switzerland to live with his son, Alfred, who was a professor of history. Alfred made it a point to mentor young Jewish undergraduates, one of whom was Albert Einstein. So you can, Stern, like Einstein, had been made a full professor of history at the Federal Polytechnic School in Zurich. The friendship between the two men began during Einstein's student years. He would frequently visit the household. They shared a passion for music. Einstein repeatedly enthused about the kindness and joviality that reigned in the family. Einstein's affectionate relationship with the entire Stern family lasted a lifetime. And if you look at Einstein's collected letters, there are quite a few of them early on to Alfred Stern. So if nothing else, you can get from Gauss to Einstein by a father and a son, which I think is a kind of nice historical thing. And one more historical thing here. Mart Stern's brother was the great-great-grandfather of Anne Frank. So you have quite a remarkable guy. And now I'm sure you want me to go back to the math. For a positive integer n, this is the Ferry sequence. I probably don't need to say much about the Ferry sequence. Let me get this straight. These are some of the properties of the Ferry sequence. And to go from Fn to Fn plus 1, you look at when the sum of the denominators is n plus 1, and then you put those in. And every rational appears. Eisenstein, who was one of Stern's friends, was interested in a question. Suppose you have two consecutive fractions in a Ferry sequence. Which denominators can eventually occur between them? And Stern answered, it's the diatomic array, because you're not necessarily adding the denominators in the same order that you would do in the Ferry sequence, but eventually you just get everything that was there. This is actually a tricky question. If you want to know if m appears as a denominator, it's not enough to find an integer r so that r over m is in between them. You need r over m to be in lowest terms. And this is an example this is one of the theses that I'm going to talk about, Grace Jaffe. If you consider the fractions 2 over 7 and 1 over 3, which are consecutive, you would think that 110 eventually appears. However, these are the fractions in the interval 2/7 to 1/3, and each one of them is reducible. So in fact, there is no fraction with denominator 110 that appears between 2/7 and 1/3. And as Grace proved, eventually every denominator greater than 110 does appear. The next historical figure was not a mathematician, but a French watchmaker named Achille Bracot, who wanted to find a way to approximate fractions and just basically added everything together the way we've been doing. He didn't prove anything, but since he was French and Stern was German, French mathematicians like to use Bracot's terminology a lot. The numerators are z of 0, 1. The denominators are z of 1, 0. The rth row of the Bracot array is exactly this, if you will allow me to say 1 over 0 as a fraction. And the construction proves that these are relatively prime. Each non-zero rational a over b occurs exactly once as s of k over s of 2 to the r minus k for odd k, where r is the sum of the denominators in the continued fraction. And we get s of k over s of 2 to the r plus 1 minus k. The first half of the row can also be written by symmetry as s of k over s of 2 to the r plus k. And to sum up, the Stern sequence can be used to write rationals to enumerate the rationals, or to write the rationals in two different ways. One is s of n over s of n plus 1. The other is s of n over s of 2 to the r minus n. And here they are in those two cases. And it's natural to want to know, how do you relate this permutation of one to the other? And it turns out that it's exactly this. You write down n, you write n in binary, you let n backwards denote n written in reverse. And if something is in the nth row in one of these arrays, it's in the n reverse row in the other way. This would have been done easily. This may have been done in the 19th century, but since they weren't talking about everything in terms of binary, it probably looks a lot more clumsy. Let's return to the Eisenstein question. Stern said the denominators which can occur in fractions are the elements of the diatomic array, z of ab. So this becomes a version of the Frobenius question, the Frobenius problem. Suppose the GCD of A and B is 1. This is the Frobenius problem. What can you say about the integers that are written as ax plus by? And the well-known answer of Sylvester is that every integer greater than a minus b can be so written. The answer to Eisenstein's question is that you want to know what integers can be written as ax plus by with x and y greater than or equal to 1 and the GCD of x and y equal to 1. And in Grace's example, the bad representations of 110 give you a reducible reducible fraction with denominator 110. And she constructed a function n of ab so that if GCD of ab is 1 and n is bigger than n8b, that n can be written as ax plus by with x and y greater than or equal to 1 and GCD equal to 1. And for the people who know about it, the Jacobs-Thal function shows up in her work. So this is that answers that question.
Well, how quickly does this function grow? I mean, is it roughly, again, linear in A and B?
No, it's a complicated, the growth is nasty. I don't think Grace is here. It's a complicated thing. I don't think that she ever exactly figured out what the growth is, but it's.
What's the sense of it? What's the worst case, so to speak?
The worst case is as A and B get larger. I don't remember exactly what it was, but Grace is working on a paper on this, and I hope.
Okay, it's worth looking at the syntactics.
It is. Halfin and Lucas looked at what I just said. Lucas did not use the term Fibonacci number, but used the Binet formula. The next example comes from Minkowski. And this is claimed to be the first math talk ever given, which used overhead transparencies. And it's the Minkowski question mark function, which is a ridiculous name, but it's built into Mathematica, so you can find it there. It's defined recursively. Question mark of 0 of 1 is 0. Question mark of 1 of 1 is 1. If you already know question mark that takes the values j over 2 to the r and j plus 1 over 2 to the r, then taking a plus c over b d gets 2j plus 1 of 2 to the r plus 1. So this
It's worth mentioning. That's the number that shows up, the next number that will show up between a over b and c over d in the vary sequence.
Yes. And this is defined only on rationals, and you can extend it to a continuous function on 0, 1. This is the general formula that appears, and it has some nice properties. This is a formula for the limiting function. Now, if you have a sequence of AIs that are eventually periodic, on the left-hand side, that happens if and only if x is a quadratic irrational. And on the right-hand side, that happens if and only if x is a rational that is not a dyadic rational. So question mark not only gives an increasing function from the rationals, the dyadic rationals, it gives an increasing function from the quadratic irrationals to the non-dyadic rationals. Question mark of the square root of 5 minus 1 over 2 is a third, for example. And question mark is singular. The derivative is 0 almost everywhere. There are dozens of papers on it on MathSciNet, but I'm running late, so I'm going to move on a little bit. The next time that I saw the Stern sequence appear was in a monthly paper by Williams and Brown. You start with 2 circles of radius 1, and then you draw that are tangent to a line. And then you draw the circles that are tangent to the previous circles drawn and the line. And what they prove is that if your original circles had radius 1 over r squared and 1 over s squared, then the smaller circle you get underneath them has area 1 over r plus s squared. So that's bringing us back into Stern land. In this particular picture, the circles have radius 1 over, well, you can read that there, which are the reciprocal squares of S of 8 through S of 16. Or by taking out the powers of 2, you see that you get all of the odds up to S of 15 as the radii. And Williams and Brown computed the sum of the areas of the circles as this nice sort of unexpected thing with the zeta function. However, they used the fact that each integer m is going to occur phi of m times s of 2n plus 1. So they're really looking at the summation of phi of m over m to the fourth, which is a nice problem from a first year analytic number theory class. And this is the general formula for that. I started to play with this I guess I'm realizing it's a long time ago, without knowing whether it was known or not. How did one figure out whether a sequence was known before the online Encyclopedia of Integer Sequences by Neil Sloan? There was the Handbook of Integer Sequences, which was a book that was written by Neil Sloan. And searching in my book, I found the Stern sequence, basically. And I decoded the reference to realize that this was an article by the topologist Georges Geram, who actually wrote 3 papers on the subject. You take a convex polygon, trisect the sides, and snip off the corners. You get a convex polygon with 2 end sides. Repeat the process. Consider the limiting figure. Don't be like that guy at Caltech who yelled out during my talk that the limiting figure is a circle. In fact, it's the least circle-like thing possible. It's smooth, but every segment contains points with 0 radius of curvature and points with infinite radius of curvature. And the reason the Stern sequence comes in is that if u and v are consecutive edges, then after you snip, the consecutive edges are u over 3, u plus b over 3, and v over 3. So you can use the mechanism of the diatomic array to get the exact formula of things. And then Geram used this to prove what he said before. And he also noticed that if you divide the sides in ratio 1:1 instead of 1:1, then in the limiting curve consists of piecewise parabolic arcs, which is kind of a nice change. And there's also an extensive literature on Geram curves in math.
Does the process depend on which polygon you started off with? I mean, different polygons give different.
No, it's pretty much depends on the ratios. So mathematicians of a certain age and disposition might remember this problem from the 1984 Putnam exam, where you take these polygons and you start with an equilateral triangle, snip off the corners, and try to find the area. Well, I was on the questions committee that year. I put that on there. This was the one part of the construction that Geram didn't write about. Each snippage removes 2/9 of the previous one, and the total removed is a computable geometric series. Eventually, I realized that I had borrowed Archimedes' method of exhaustion, only steal from the best. But I was pleased with myself for being able to write a B6 Putnam problem theoretically accessible to a high school student with no exposure to advanced mathematics or obscure plane geometry theorems, one of the problems I have with the Olympiad, and which it turned out only 13 people solved. Dijkstra independently came upon the Stern sequence. I'm running a little late, so I'll just say that once he discovered somebody else had looked at it, he said it was fun. Karlitz wrote several articles on a function related to Stirling numbers of the second kind. And as part of an undergraduate research project, Doug Lind established that this function was basically the Stern sequence and reinterpreted some of the problems of the Stern sequence, which he called A of n. This wonderful book, Concrete Mathematics by Graham, Knuth, and Potachnik, contained a section devoted to developing what they call the Stern-Bracot tree. There it is. And somebody was asking me about the Kalkin-Wolf tree. Well, this was about 10 years earlier. It's really the same thing. And then every rational appears here. I should mention 3 monthly articles. The first one in 1929, when he was a grad student, D.H. Lamer summarized the facts about the Stern sequence, and that the largest values in the first quarter form the Lucas sequence. Sam Northfield wrote a survey article updating Lamer's with connections to the Minkowski question mark function and the more combinatorial interpretations I'll talk about soon. And then Kalkin and Wolf wrote the book Recounting the Rationals, which summarized and publicized a lot of this material. And Herb Wolf vehemently objected to my using the term Stern sequence. He said Stern didn't call it a sequence. But my feeling is that the results are more important than the packaging. Let me go through the generating function. You use the recurrence to find the generating function and get a nice expression. And in this way, you can interpret S of t as, well, the number of ways of writing S of n is the number of ways of writing n plus 1 as a sum of powers of 2, where you allow digits of 0, 1, and 2, which I think is sometimes called a hyper-binary representation these days. Variations of these ideas led to several dissertations. Melissa Dennison, I gave her the recurrence with the second halves reversed, b of n plus 1, and b of n. And you have actually 2 parameters that are in this discussion. And forgive me on this, because it's the opposite of the Stern sequence, I called it the Bow sequence. And she was willing to accept that as the title, and I think it stuck. And with a particular choice of initial conditions, this counts the number of ways of writing n as a sum of powers of 2 with coefficients 0, 2, or 3. Melissa proved that the sequence mod 2 is periodic mod 7. Then, using basic properties of Z2 of X, Melissa, Katie Anderson, Jennifer Lansing, who were 2014 students of mine, and I proved that for any finite set of non-negative integers containing 0, if you define FA of n to be the number of ways to write this, then FA of n mod 2 is periodic, although the period might be weird. For example, for 0, 1, 4, and 9, the period is 84. Katie subtly analyzed the patterns of even and odd elements in the sequence and constructed families so that the proportion of odd values goes to 1 as m increases. She did a lot of other things as well. Jennifer looked at the sequence 1/2 S of 3n and computed the kth largest value. The maximum is fr plus 2. The second largest value is fr plus 2 minus fr minus 3. The third largest value is written there. So I'm going to have to hurry up a little bit. Wapawi looked at writing.
Excuse me, Bruce.
Yeah.
Since we're online, there's no need to rush. Time is flexible.
Okay. Well, I'll try not to. I'll try to finish by 3. Whipple, we looked at the expressions of S as a sum of powers of 3 with digits 0, 1, and 5. I wanted to take something that was 0, 1, or congruent to 0, 1, or 2 mod 3. That was a nice example. It turns out that n either has no such representation or exactly 1. And the number of representable n less than n, the density of that number is periodic in log n, varying between 5/8 and 3/4. They're arbitrarily long blocks of integers that do or don't have such a representation. Another Putnam problem. How many ways can you write n as a sum of powers of 2 if you allow the digits of 0, 1, 2, and 3? This a lot more people got this. There's a natural recurrence that leads to the answer. You can use the generating function. Combinatorialists like combinatorial proofs. Since epsilon I isn't 0, 1, 2, 3, we can write uniquely epsilon I as 2 alpha I plus beta I. So n becomes twice a number plus another number. How many ways can we do that? Well, R has to be in this set, so that's how you get floor of n over 2 plus 1. The Stern sequence mod D, let's just say I used a Markov chain to look at this. This is the pattern of what happens if you look mod 3 for S of n and S of n plus 1, where blue is going to the left, R is going to the right. And I didn't write 3 in there. All transitions have probability 1/2. And I have to tell you, this diagram was not drawn using AI. It turns out that the number of integers where f of n is congruent to 0 mod 3 is a quarter n plus O of root n. And amazingly enough, the number congruent to 1 mod 3 and the number congruent to 2 mod 3 are nearly equal. They differ by only a finite number. More importantly, you have these formulas for from the Stern recurrences, which says that 3 divides S of n if and only if 3 divides S of 2n, S of 8n plus or minus 5, 8 of n plus or minus 7. Notice that this is an exact covering system. And so this lets you define a recursive set to determine whether 3 divides S of n. And one of the things that you can do is associate a graph. If this is an exact covering system, you make edges from n to di n plus ai. Each vertex is out degree r in degree 1. And you can analyze these graphs. But here you're allowed to take negative di. That usually don't look at n is congruent to 3 mod minus 2, but you could. And that makes things much more interesting. Dana Neidman did a complete analysis of the digraphs where R was 2. And I took this picture from his thesis. This part in the upper right are the numbers where 3 divides S of n. That's what this graph looks like. I think maybe I'll skip this. Dana proved that every integer can be written in this form if and only if a can be written as 1 plus or minus 3 to the m. This is just using the analysis of the graphs that I skipped over. And Wapawi looked at graphs with those edges and showed that there are 2 components which are very similar to each other. Now, let me change the topic. This is a picture of what the Stern sequence looks like as n goes from 2 to the 15 and 2 to the 16. As I said, the maxima get bigger with respect to the average than the minima. That looks kind of bad. The cumulative summation function looks much nicer until you look at it carefully. Here I'm looking at the difference from the straight line. And there is a limiting function that comes up to the summation. It's not hard to get exact values. These aren't so bad. It's just incredible that f of 1/7 is 67 over 622. You almost think that you made a mistake, but I found this 2 different ways, so I think it has to be correct. And then that function f has the fact that its derivative at every dyadic rational k over 2 to the m is 0, and it's singular at every k over 3 to the 2m, where the GCD of 3 and k is 1. So this is really an elaboration on what Durham did. that shows how you can have nice and not nice things, just both basically dense. One of the parts of the proof, I didn't invent this. I saw somebody in our seminar used it as kind of a trapezoid rule of summation where you count the n sum n's with a weight at 1/2. The advantage here is that they're completely additive, and also they behave well with respect to the Stern sequence. Okay, so now the last topic is the generalization of the Stern sequence to polynomials, where you replace s of 2nx with x times, you change this recurrence by putting an x in there. These are what the polynomials look like. I'm only putting in the odd ones. There are a lot of properties. If you put an x in one, obviously you get back s of n. If you put an x equals 0, you get 1 or 0, depending on whether n is even or odd. If you put an x equals 2, it turns out that s of n2 is n, which proves that these are all different. And also that if s of n divides s of m as a polynomial with integer coefficients, then n has to divide m. You notice so s3 divides s9 and s15, but s5 does not divide s15. This is not an if and only if statement. One more value, it turns out that s, if you evaluate it at -1, if n is 3k, you get 0, 3k plus 1, 1, and 3k plus 2, -1. So s of 3kx is always a multiple of 1 plus x. Putting an x in 1, this gives you another proof that s of 3k is even. The degrees of these polynomials are very well behaved. This equation comes from the recurrence. An easy induction gives you that. So you can construct the set of polynomials that have, of these Stern polynomials that have degree d. There are 3 to the d Stern polynomials of degree d. A third of them have even degree, 2/3 have odd degree, which might sound crazy, but adding it up, it becomes infinite. This is the range of n. The sum of the indices of the polynomials of degree d is 10 to the d. So the average one is like 10/3 to the d. The number of monic Stern polynomials of degree d satisfies a recurrence and grows like 1 plus √2 to the d. So the probability that Sn is monic goes to 0 as n goes to infinity. This is what s of 2 to the r minus 1 is. And if you put an x equal to 1, you see r, and we just accept that the value of this is r when x is 1. If you look at the maximum value, the value of n that gives you the maximum of the Stern sequence, it turns out that this has a very nice expression in terms of a polynomial in several ways. And the roots of SMR are ultimately dense on -infinity to -1/4. But these are exactly computable. Many of the formulas for the Stern...
Wasn't that last thing that more or less a Chebyshev polynomial?
It's...
No?
Yeah, I think it was...
Some variant of the Chebyshev polynomial?
Yeah, I'm pretty sure it's a variant of the Chebyshev polynomial. Many of these formulas carry over to the polynomials, and then if you put x equal to 1, you get back the formula for the Stern. This is the generating function. This is the coefficient of x to the r and Sn plus 1. A polynomial is unimodal if its coefficients are non-decreasing for a while and then non-increasing. It's empirically true that each Sn of x is unimodal, and David Altizio, who defended in April, and I conjectured that this is true for each Stern polynomial, but we have not proved it. The matrices carry over pretty well. One of the closed forms comes over well. S of n over S of 2 to the r minus n is this expression here where AI is replaced by this polynomial xai, and the 1 is replaced by x to the ai. When x goes to 1, you get back the previous form. And this is a way of calculating what S of 25 and S of 7 is from the continued fraction. If you do the reversal of the Stern polynomials, then you get a monic polynomial. And this proves that the zeros of S2n plus 1 are reciprocals of algebraic integers. Here is a picture of the zeros for n going up to 2 to the 16. I call this the horseshoe crab. As I said, I grew up on the East Coast, so sort of saw horseshoe crabs. Let me give you an expansion of what it looks like over here. So these two, the points that have little holes around them are the cube roots of 1. And there are lots of conjectures about this. The 1 is going to be a limit of zeros, but 1 is positive, so that can't be a root of any Stern polynomial. You get minus infinity to minus a quarter as in the closure. David conjectures that Z bar is connected. He's proved that there's zeros with arbitrarily large imaginary imaginary part, and we conjecture that there's some sort of computable bound that will bound the imaginary part based on the real part. Gowron proved that there are no real roots of Stern polynomials in this range, and David extended it to modulo C less than or equal to a quarter. And the big conjecture is that there are no zeros for real part greater than or equal to 1, which I've checked up to 2 to the 22. And I definitely expect this is true. He also proved that if z minus 2 is less than or equal to 1, there are no zeros for any Stern polynomial. And this implies a conjecture of Ulas, and Schinzel. If P is prime, then SP of X is irreducible. And David put his paper on the archive in the last week, so you can find it there. What I've been fascinated by for a long time is how Stern polynomials factor. If you take this formula and put in k equal n, you find the fact that S of nx will divide S of 2 to the r plus or minus 1 nx if r is big enough. And that means that Sn of x divides infinitely many S of mx. And you can use a recurrence to prove that the number grows at least like some positive power of n. But the empirical evidence is that every factor except 1 plus x to the first occurs with density approaching 0 as n goes to infinity. So here is the definition of a Stern factor. The cyclotomic polynomials are all Stern factors, and they can have arbitrarily large coefficients, both positive and negative, which means that there's no a priori bound on the coefficients of any polynomial that divides a Stern factor. But on the other hand, taking the reversal of a factorization, the reversal has zeros that have to lie in z less than 4 because they're outside the circle z minus less than or equal to a quarter. And because the coefficients are elementary symmetric functions, this proves that for each degree, there are only finitely many possible polynomials. I have done an exhaustive check and making my computer crash and restarting it and going further and having it crash, etc., having it work many nights. I found 17 irreducible quadratic factors. The last appearing quadratic makes its debut at about 2.9 million. And the fact that there's nothing new between 2.9 million and 2 to the 30 makes me think that maybe that's all there is. 1 plus x is special. That's not so interesting. The number of multiples of 1 plus x squared has an exact formula, and you can see that this number shows that the density of factors of 1 plus x squared is O of n as you get large. And then this was just strange. Not only was this true when x is equal to 1, but actually the Stern polynomial at 3 to the r is 1 plus x to the r for r equals 1, 2, 3, and 6, and no other r up to 600. And then the final formula, I've done a lot of formulas in my life, but this one I think is the most amazing. So you take 2 to the r minus 1, 2 to the 2r minus 1, 2 to the 4r minus 1, up to 2 to the m times r minus 1, and x. Then that's one factor to the mth power, another factor to the m minus first, going all the way down times Sn of x, where f1 and f2 are kind of nice, and f3 and so on are sort of nasty. And the consequence of this is that any factor of any polynomial of this form can appear somewhere in the Stern sequence to an arbitrarily high exponent. In particular, every cyclotomic polynomial is a Stern factor. And by lots of individual calculations, I checked that this is true for every linear and known quadratic. And I have a conjecture that every Stern factor appears to an arbitrarily high power. I also have a conjecture that if you pick any m and n, you can find a Stern polynomial that the product S of m, S of n divides. I've verified this up to 24, but it's not very nice. The smallest multiple when m is 7 and n is 21 is this number at about 22 million. I know there's something that works for 15 and 19, and it's between 67 million and something times 10 to the 14th. I had sort of a tricky thing that got me this value. I'm currently stuck on 2125, is why I stop at 24. And as I said before, my computer is very patient. But these conjectures are misleading. For random large n up to the factor of 1 plus x, Sn of x is usually, up to a factor of 1 plus x, Sn of x is usually irreducible. I took 2,000 random odd numbers in the interval 2 to the 63, 2 to the 65. And this was true for all but 55 times, and the exceptions all just had a higher power of 1 plus x. Now, I should say, by looking at these values, Gowron proved that the probability that 1 plus 2x or 1 plus 3x divides Sn of x goes to 0 as n goes to infinity. My conjecture is that the probability that Sn is either irreducible or 1 plus x is irreducible goes to 1 as n goes to infinity. This is stronger than saying that any particular factor occurs with density 0. And I have one more conjecture. I promised Sergei Gelfand of the AMS Press for about 10 years that I would write up for publication the Stern notes from topic classes that I taught in 2006 and 2012 here, and have forced my students to read for the last 19 years. The last conjecture is that I will start writing the book soon. So thank you for your attendance and patience, and I did beat 3 o'clock.
All right, thank you for a very nice talk.
I was going about the book, but to answer that, I don't need to.
Any questions for Bruce?
Sorry, I have a question. First of all, I would like to thank you. It's very nice and
Thank you.
a little bit unexpected. I have two questions. As far as I understand, the Stern numbers, the Stern function is not multiplicated.
Yes, that's correct.
Okay, and another question is the following. I have seen that the summation, so-called the summatory function, is almost linear. Is it proved, or it is calculation, the justification?
Well, I was able to prove that was approved.
It was proved, yeah?
Yeah, not public, just no referees.
Mhm. Yeah, thank you.
Other questions? If not, thank you again, Bruce, for a lovely, lovely talk.
Things that I think you can order on print by demand from Amazon.